Hello, in this video I'm going to review factoring by grouping. First I'm going to show factoring by grouping when we are trying to factor cubic polynomials, or polynomials with a degree even higher than a cubic. But then I'm going to also take this a step back and apply it to some Algebra 1 problems that in Algebra 1 are a little more difficult when we have a coefficient on the x squared term that is not a 1, and show you how you can use grouping to navigate those in a way that's not just guess and check. But first, let's review how to do grouping if we have a polynomial with 4 terms and a degree of 3 or higher. So first, there we go. What I'm going to do is I'm going to go through this process, but I'm going to do it with all 3 of these examples at the same time so that you can see, you can kind of compare and contrast how each step might look different depending on the actual expression or equation that you're working with. So my green expression is x cubed plus 2x squared minus 36x minus 72. My blue expression is 3x to the 5th minus 15x to the 4th minus 75x to the 3rd plus 375x squared. And my purple equation is, or my purple expression is x cubed minus 4x squared plus 9x minus 36. So for all 3 of these, anytime I am factoring anything at all, I always want to ask myself first, is there a greatest common factor for the entire expression? Because I always want to get that out of the way first if it exists. So in my green expression, I'm going to look at the variables first. I see that not every term has an x in it. I have a constant term, and all my other terms have x's, so there's no GCF with an x. And some of my terms just have a coefficient of 1. So it doesn't appear that there is any useful greatest common factor across the entire expression here. Looking at my blue, I see that every single term has at least an x squared in it. And I also see that my coefficients are all multiples of 3. So I am going to say I've got a GCF of 3x squared. Before I even do my grouping, I'm going to take that GCF and factor it out front so that I have something simpler to work with. So if I factor out 3x squared from all 4 terms, that leaves me with x to the 3rd minus 5x squared minus 25x, and then plus 125. So in the blue expression, there's a GCF for the entire thing. Always start by asking yourself that. And then in the purple, I have a constant term, so I know I can't take an x out of everything. Once again, I have this 1 in the front, so my coefficients don't have anything in common. So my first step will only work for the blue. And I'm just going to draw a line there. If there is a greatest common factor for the entire expression, always begin with that. And then now let's just bring everything down and continue from here. So our blue expression, we factored out a GCF. Our green and our purple, that was not relevant. What we're going to do next is we're now going to split our expression into kind of a front half and a back half and just look for the GCF of 2 terms at a time. So in my green expression, what that means is I'm just going to look at these guys. X cubed plus 2x squared. I'm going to notice that both of those have an x squared in them. So the GCF of the first 2 terms is x squared, which leaves me with x plus 2 just for the front. I'm going to do the same thinking for my back two terms, negative 36x minus 72. So notice that this one starts with a negative. If there's a negative, I'm going to include that in my GCF. So the GCF of the back two terms is that both of those are multiples of negative 36. So I'm going to factor out a negative 36, and then I'm noticing that that leaves me with x plus 2 again. So I've kind of split my expression in half, factored a GCF out of the front, factored a GCF out of the back, and I know that this is starting to be successful because I have x plus 2 both times. Factoring by grouping will not work unless when you factor out that front half and back half GCF, you get the same binomial left behind in your parentheses. So it's possible that you may have a problem that does not work with this method, but the entire point of grouping is you are looking for that binomial that can be factored out twice. So let's do the same thing with the blue step. I'll do it a little more quickly with these two other examples now that you've seen it. So my GCF stays here. That's just living there. Now I'm working within the rest. If I focus on my first two terms, they both have an x squared, which leaves me x minus 5 behind. And then my back two terms are both multiples of negative 25. So that leaves me with x minus 5. So I see once again, when I took out the GCF of the front and the back, I ended up with matching binomials, x minus 5 and x minus 5. That's a good sign. And then finally, for my purple example, focusing on my front two terms, if I factor out an x squared, that leaves me with x minus 4. And then on my back two terms, if I factor out a positive 9, that leaves me with x minus 4. So once again, I have, you can see in all three of these, the key step in grouping is that we are aiming to take a GCF out of the front and then take a GCF out of the back such that you end up with these matching binomials, x plus 2, x plus 2, x minus 5, x minus 5, or x minus 4, x minus 4. Now what we're going to do is we're going to do our grouping step. In the grouping step, I'm going to take my two, I'm going to take like my pink pieces, my x squared and my negative 36, those pieces I factored out of the front and back, and those I'm going to put them together. And the reason I'm putting them together is you can think of this like I am multiplying both of those things by x plus 2. They are not like terms with each other. X squared and negative 36 are not like terms, but both of them are being multiplied by x plus 2. So I can abbreviate this by saying I have both of them. They are both being multiplied by x plus 2. So I've rearranged the statement to say the same thing, but in a different order. X squared and negative 36 are both being multiplied by x plus 2. So in our blue example, that guy's just going to live in the front the whole time. X squared and negative 25 are both being multiplied by x minus 5. In my purple example, x squared and positive 9 are both being multiplied by x minus 4. So those two steps that I just completed, those are the key thing for grouping. From this point, I'm going to see if I can continue factoring further using my Algebra 1 skills, but these two steps here are the kind of like meat and potatoes of factoring by grouping. What I want to ask myself at this point is now I want to look at each of my individual factors and ask myself if any of them could be factored further. Sometimes this is possible, sometimes it is not. It all depends on the expression you're working with. So if I look at my first expression here, I have x squared minus 36 and I have x plus 2. X plus 2 cannot be factored any further. It's just a linear term and a constant term. But x squared minus 36, I want to always have my eye out looking for differences of squares. So this is a difference of squares. I have x squared and 36 is 6 squared. So a difference of squares, I can factor this into x plus 6, x minus 6. Because my constant terms will multiply to negative 6, my linear term will add to 0. 6 minus 6 gives me 0. And then x times x gives me x squared. And then I've still got that x plus 2 tacked on the end. Now I am what we call factored completely. I have broken this into as many factors as is possible. None of this could be broken down further, so that is complete. In my second example, my 3x squared, that's as factored as it's going to be. It's got a multiplicity of 2. I could rewrite it as 3 times x, but that doesn't really help us. So I'm going to keep that the way it is. X squared minus 25, I see I've got another difference of squares. So I can rewrite that as x plus 5, x minus 5. And then I still have that blue x minus 5 on the end. What you'll notice here is now I've factored my difference of squares, and it gave me, now I see there's one factor that is repeating. So x minus 5 ended up in this result twice. So now, if I'm thinking about multiplicity and bounces and crosses, I can rewrite this final answer as 3x squared, x plus 5. Then I could say x minus 5 squared. It's x minus 5 squared because I have two x minus 5 factors multiplied together. So I have a multiplicity of 2 at that factor. That means I'm going to have a bounce at the 0 that's associated with that factor. Now I have finished factoring this one. Nothing could be broken down further. I've combined my repeated factors into a multiplicity, and that's something I could sketch the zeros and talk about the bounces and crosses nice and easily. Finally, our last one. So in this one, I'm tempted to do a difference of squares because I see that number 9. However, notice that this is x squared plus 9. X squared plus 9 is not a difference of squares because we have addition, we do not have subtraction. So I might want to check my work to make sure, but this is an important example because not every factoring by grouping will magically lead you to a difference of squares. Difference of squares are important to look out for, but they are not always there. Like maybe this one, this is just as far as we can go. So thinking about x squared plus 9, this binomial here, we cannot factor any farther. We will talk about what this binomial means in terms of x-intercepts later in the unit when we get to imaginary numbers. But for now, there's nothing I could do with x squared plus 9. So my completely factored form is, I don't like that. Make it colored. Make it purple. My completely factored form is this. It's not a difference of squares. Nothing else is factorable. I am factored completely. So hopefully what you can see with these three simultaneous examples is the general thought process is the same, but your individual expression might have different steps or it might not. The green expression did not have a GCF. It was groupable. It did have a difference of squares, but it did not have any repeated factors. The blue expression did have a GCF. After the GCF, it was groupable. Once we did the difference of squares, we had a repeated factor, so we ended up with a multiplicity of 2 on one of our factors. The purple had no GCF. It was groupable. Once we grouped it, it did not give us a difference of squares, so we were kind of finished early. All of these are possible and all of these are correct. So you want to think about each of those steps, but you don't want to assume they will all always happen. Always look for a GCF first, and then When something is not available, move on to the next tool in your toolbox. One other situation I want to apply this to, so these are all factoring by grouping with cubics. And in cubics, you're starting with 4 terms. So it's kind of already easy to split this into a front half and a back half. I want to show you that you can use this grouping strategy for trinomials when a is not 1. So you may have done these in Algebra 1, kind of using guess and check or just the box method to try to figure things out. But what I want to show you is that when we have that pesky 3 in front or that pesky 10 in front of our x squared, we can use this grouping strategy to factor difficult quadratics. So what do I mean by that? When we factor a quadratic where the coefficient on the leading coefficient is 1, so let's say we're factoring something like x squared plus 6x plus 5, right? When we're factoring something like this, we're just looking for what multiplies to 5 and adds to 6. When we do that, we could make our list of factor pairs. We could say, okay, I have 5 and 1, 1 and 5, -1 and -5, -5 and -1. So those are all the factor pairs that give me 5. The pair that adds to 6 is right here. Once I've found my pair, then I can write my factored form, x plus 5, x plus 1. So when I do not have an a value, I can just think what multiplies to my constant term. However, when we have an a value like 3 or 10 in the front, it's not so simple because that's going to affect how everything combines when it's distributed or factored. What we're going to do instead is we're still going to ask ourselves, we're still going to make a list of factor pairs, but instead I'm going to say, I'm going to take this a value and my constant term. I'm going to multiply them together. So I'm going to say I want things that are factor pairs of 3 times 10. So if I multiply 3 times 10, I get 30. 3 times 10 equals 30. And then I'm going to ask myself, what are all of the pairs of numbers that multiply to 30? I could do 1 times 30. I could do 2 times 15. I could do 3 times 10. I could do 5 times 6. And then I could switch the order, do 6, 5, 10, 3, etc., or -6, -5, -10, -3. So I won't write out that entire list, but this is kind of my basic set of pairs, and then I can play around with negatives if I wanted to. So I know that my factoring is going to involve those pairs of numbers somehow. Now I'm going to ask myself, if once I did this 3 times 10, found those factor pairs, which pair of numbers adds to 11? So looking through my list, 1 plus 30 is not 11, 2 plus 15 is not 11. However, 5 plus 6 is 11, right? So I found my factor pair, but this is when I'm going to do my grouping step. 5 and 6 will allow me to factor by grouping if I split my linear term into a 5 and a 6. So I'm going to rewrite my quadratic as 3x squared plus 5x plus 6x plus 10. I didn't do any factoring. I just said, okay, I found my magical pair. I'm going to split that linear term into 5x and 6x. It doesn't matter which one I put first. I can put the 5x first or the 6x first, and we'll see that the grouping will work either way. Now, I'm going to treat this like I treated my cubics, and I'm going to do factoring by grouping. So here's my front half, here's my back half. In the front half, both of those have an x, but there's nothing else they have in common. So both of those are x. That leaves me with 3x plus 5. On the back half, both of these are multiples of 2. That's all they have in common. But notice, when I take out my 2, I get 3x plus 5. So if I do my grouping strategy, Now I have factored a trinomial where a is not 1, and I didn't have to do all the guessing and checking that you may have done previously in Algebra 1. So to recap my steps a little bit here, I multiplied my constant term times my quadratic leading coefficient. That gave me 30. I asked myself, what are all the factor pairs of 30? I need numbers that will multiply to 30, not to 10, to 30. Then I chose the pair that adds to 11, and I split my 11x into that pair, 5x plus 6x. So I just kind of like did combining like terms in reverse. Took that 11, split it up. Then I used my grouping strategy, and if I chose my numbers successfully, and if this is factorable, when I do my grouping strategy, it will give me the factored form of 3x squared plus 11x plus 10. So let's try that again over here. I have 10x squared plus 13x minus 3. My first step, I'm going to take that negative 3, multiply it by 10. That gives me negative 30. So for negative 30, I could have negative 1 and 30. I could have negative 2 and 15. I could have negative 3 and 10. I could have negative 5 and 6. Or I could have negative 6 and 5. Negative 10 and 3, negative 15 and 2, negative 30 and 1. So I'm going to create my list of factor pairs. I'm going to ask myself which of these pairs adds up to 30. So looking through, 15 minus 2 is 30. So that's going to be my magic pair. And I'm going to split my linear term into 15x and negative 2x. So I'm going to keep my quadratic term. Then let's put the 15x in front. Why not? Doesn't matter. Either way, it'll work. 15x minus 2x. So I've split this. 15 minus 2 gives me 13. So I know I'm writing something equivalent. Now I have 4 terms. If I have these 4 terms, I can do my factoring by grouping. I'm going to take my front terms, factor out their GCF. Their GCF looks like it is 5x. That leaves me with 2x plus 3. The GCF of the back half is just negative 1. They're both negative, so I'm going to take out the negative 1. That leaves me with 2x plus 3. And then you see my grouping worked. I have 2x plus 3, 2x plus 3. It was very important that I took out the negative. If I did not take out the negative, then my grouping would not have worked. So then I can collect my pink terms. Both 5x and negative 1 were multiplied by 2x plus 3. And then here is my factored form. So if previously you've dealt with these trinomials by just kind of like staring at a box method and kind of like guessing and checking until you can make it work, factoring by grouping can be a nice strategy for these. Because even though you have to make that entire factor list, it gives you a reliable method that, if it is factorable, will always show you the set of numbers that will factor. So the time when you will need to use this is with cubics. But it's nice to apply this strategy to difficult Algebra 1 problems like trinomials when a is not 1. Because it can give us a reliable procedure to figure out the two factors.